Okay, so we have, this is a series, you see it's a sum of terms, and it's going to go on and on. So we want to get this thing looking like something that we know. So we're going to make it into, use this sum, n equals 1 to infinity. And let's work on the numerator first. So what do we got? 4, 16, 64, 256.
2 to the n.
He wants 2 to the n.
4 to
4 to the n.
even better.
Okay, we're just looking at the numerator.
4 to the n. 4 to the n.
Yeah, so it looks just like 4 to the n.
So we want to negative 4 to the n too. Negative 4 to the n.
Okay, but then it alternates, right? This is called an alternating series because every other one is positive and negative sign. So someone suggested negative 4 to the n. Does that work?
No, negative 1 to the n times that.
Okay, someone has suggested negative 4 to the n. Does that work? So if n is 1, we get negative 4. If n is 2, positive 16. Then negative, yep, so that works. But then multiplying by negative 1 to the n is the exact same thing. Negative 1 to the n times 4 to the n is negative 4 to the n. So it looks like our numerator looks good. What about the denominator? 9 to the n. And we're not going to put the negative in again. If we put the negative in again, then we get all positive terms. So just do the negative in the numerator. It looks like we got 9 to the n. Okay? And so we want to get it into our form a r to the n minus 1.
Well, if you can go into that form.
If. Can it? Sure it can, right? So this is negative 4/9 to the n. And so if we want this to be to the n minus 1, in essentially what are we doing? We're pulling out a negative 4/9, right? We're pulling out one factor of negative 4/9. We did a couple of these on Friday. So we're pulling out 1, and that leaves how many? N minus 1, right? So here I have n negative 4/9, and here I have n negative 4/9. It's just one of them times negative 4/9, not n minus 1 of them. And that makes a total of n of them, just like this. Right? Multiply together. So if you think in terms of what exponents means, that helps you. Because what does this mean? It means multiply that together n times. So imagine, negative 4/9 and negative 4/9. You've got n of them. Well, I need n minus 1 of them. That's 1 less. So I can just multiply that by 1 more, and I have n of them. So you just really got to think of the meaning of exponents. As repeated, how many times you're going to multiply by that factor. Okay, convergent or divergent. So this is now exactly in our geometric series form. Convergent or divergent. Convergent, Brandon? Why?
Because R is between negative 1 and 1.
That's right. That's between negative 1 and 1. So therefore, the sum is?
So negative 4 over 9 times 0.
No. A over 1 minus r is what we showed in class. That a convergent geometric series equals A over 1 minus r. What is A? Negative 4/9. What is r? Negative 4/9. Does it make sense? Any questions? All right, let's check.
So
Got it.
the only time that we're not going to have A and R be the same is if there's some other random factor or random.
Oh yeah, that's only because we're in the situation where we're factoring one out.
Yeah.
So if these were all multiplied by 3, or not 3, say 5. So if every one of these is multiplied by 5, then you get 5 times negative 4 over n. And then your a would be 5 times negative 4 minutes.
Sure. Okay. So then it's not helpful to think of a rule in terms of n. We want to get into n minus 1 form.
Yeah, so the way we've seen geometric series is a r to the n minus 1, or n starts at 1.
Okay.
Okay, let's do one more of these. The cause difficulty. 12. Okay, so 12, this gives you a sequence. It asks about the limit of the sequence, the limit of the series. So really, it makes more sense to talk about the sequence first, because we know if we know something about the sequence, then we have these, we make these conclusions about the series. So what about the sequence? 7n over quantity 4n plus 7.
It'll converge to 7/4.
He wants it converging to 7/4.
Right.
That should be easy. We should all see that this converges to 7/4. You can either think of this as a rational function from pre-calc. You have f of x equals 7x over 4x plus 7. And so this is a rational function with the degrees being the same. And therefore that limit is the ratio of the coefficients. That thing goes to 7/4. Or if you want to use L'Hopital's rule, you can use L'Hopital's rule. Because you got this is the what is it called? Right. Infinity over infinity. No, I think the word. Anyway, so infinity over infinity means you can use L'Hopital's rule. Indeterminate form. It's an indeterminate form. Infinity over infinity, and so take the limit of both, you get 7/4. Okay, and use the L'Hopital's rule. Either way, that thing is going to 7/4. So the limit of the sequence is 7/4. Okay, now what about the series?
We need to waste our time.
What's that?
We don't need to waste our time.
The sum of the series is 1.
It can't.
It has to diverge because the sequence doesn't go to 0.
Right. So yeah. So think about what's happening here. The numbers are getting indistinguishably close to 7/4. And when we're adding all the numbers together, so in the end, what does this series do? It just keeps doing what?
It keeps adding 7/4.
It keeps adding a number like 7/4 forever, right? Because the sequence gets indistinguishably close, the values of the sequence get indistinguishably close to that, and now we're going to add them all up. So after so many terms, it's like we're adding 7/4 plus 7/4 plus 7/4 plus 7/4 plus 7/4. What's that series going to do? Diverge, and then now they want a little more specific than that. They said if divergent, enter I and F if diverging to infinity, and that's what it's going to do. Okay, questions on this one? Good, great, basic problem there. So the only chance the series could converge is if in the end it's like you're adding 0, right? It's like you're adding smaller, really small numbers. So that's the principle again, that sequence has to go to 0 for the series to converge. Is that enough? If the sequence goes to 0?
No.
No, it has to go 0. Also has to go fast enough. So we saw like a harmonic series doesn't make it to 0 fast enough, and so the series is still infinite. But if it's a p series or a geometric series that meets the conditions, gets to 0 fast enough, then in the end it's like adding 0, adding 0, adding 0, just a little teeny bit so that that series levels out to a finite value. Okay, questions on these basic review things? Anybody? Okay, so let's.
We're going to get into some physical applications.
Not many. There's some, but in this course, not many.
But they're used, not the series.
Yeah, there are applications of them. It's not, like we saw the integral had all the engineering. It's not rich like that.
Sure.
But yes, there is use in the world for these things. Okay, so let's go on and talk about what's called alternating series. We've already seen alternating series. It means that the sign, the sign changes from one to the next.
Is it always that instead with one?
What's that?
Is it always that n starts with one?
No, it could start with 0. So let's.
So when given a list of numbers, like if I'm given a sequence, then I should always take that as n equals 1, as starting from n equals 1, right?
So sequences normally start with n equals 1, and that's how. So that's how we introduce series. But if you want, let's see. But series, you can start the index at anything you want. You can start it at 0, or you can start it at 2. It's just, for sequence, we normally start with 1 because we think of that as the first term. First term, second term, third term, fourth term. But then when you get to series, we kind of start by doing that, n equals 1, because they came from sequences. But then with a series, n can start at 0. So let's do that here.
Well, couldn't n start at anything if we're talking about infinite sums?
Right, exactly.
That's nuts. You can go from infinity to infinity.
So if let's just, just for sake of argument here, we'll just call it starting at 0. Okay, so n can start at 0. And so then b0 minus b1 plus b2 minus b3. So this is the idea. And we've seen these before. They alternate in sign. Okay, they alternate in sign.
So is it possible for different students to have different answers when it comes to coming out with the formula?
I'm sorry?
Since you're saying that we can come up with any starting from anywhere, right? So can we have, is it possible for us to have different students have different,
No.
like if I said the sequence with a 0, and the person that starts with the one, will it be the same or that?
I don't understand your question. So when you're given a sequence or a series, there's going to be a starting n value, and so it's the same sequence or series for everybody. You don't. It's not. You can't change the problem.
Like the problem that we just did,
Uh-huh.
we give you numbers maybe 1, 2, 3, 4, 5, and then they say that come up with a formula that,
Right.
then, if a person, if I, for example, start with n equals 1, and then the first student starts with n equals 1.
You'll get the same final answer.
Or same.
Yeah, if you're consistent, as you start with n equals 1, you do the whole problem consistently with n equals 1, and other students chooses n equals 0 to be the first one,
Yeah.
and they're consistent, the whole problem starting with n equals 0, you get the exact same
I
answer.
was just thinking of the formula itself. The an equals something. Is that going to be the same or obviously that won't be different, right? Since you said different points.
But if you're consistent in the whole problem with what you choose, then it's the same sum, you're going to get the same answer. It doesn't change the sum dependent on where you start the index. It doesn't change what the sum is. Yeah. Okay, so then we have, so this alternating series. So the alternating series test says that if Bn is greater than 0, so meaning the whole sequence is a positive sequence, then the series is convergent, then the alternating series is convergent. If okay, so the first thing you gotta see here is, actually, I don't have to- Okay, the sequence Bn is not alternating, right? So we're making it alternating by putting the negative one ahead. But this Bn is not alternating. That's all positive values in the sequence. So when does the alternating series converge? If that sequence is decreasing, first of all. So the next is always less than or equal to, greater than or equal to. Sorry. It's decreasing. I got the gist of it right, and I put the wrong symbol here. It's a decreasing sequence.
So the next term is less than the preceding term.
Right. So that means that you're always, it's always decreasing and positive. Okay, always decreasing and positive, and at that limit of the sequence goes to 0. So all you need now, if it's alternating, is for the limit of the sequence to go to 0. If you put the alternating effect on it, then that series will converge.
And by decreasing, you mean the numbers that have the same sign in front of them, like a positive and a negative.
What's that?
What do you mean by decreasing? Is it
Decreasing. The next one is always less than the previous. 10, 9, 8, 7, 6. Those are that's a decreasing sequence.
Also without thinking of the positive or negative, right?
This has nothing to do with the positive or negative.
Oh.
Bn is all a positive sequence.
Oh, yes.
Bn is all positive, and then this makes it alternate. So Bn is a positive series. Okay, so for example.
Wait, so what are we testing? We're just testing for convergence?
Yeah. Oh, did I not? Did I write that? Yeah, is convergent, if. Yeah, right here. Is convergent, if. Okay. So what is the Bn here? And what is that?
That's a sequence that converges to
Harmonic.
0.
Harmonics.
That's the harmonic, right? That's the harmonic sequence. So does this thing converge or not?
No, well, it doesn't. I think it's one.
So what is this? This is 1 over 1 plus, or sorry, minus 1/2 plus 1/3 minus 1/4, etc.
Isn't it?
Divergent or convergent?
Do we shift the signs 1 over?
What's that?
Because the first one is negative 1 to the power of 1 minus 1.
0.
Okay.
Convergent or divergent? So this is like our harmonic series, but it's also alternating. Remember our harmonic series, which is 1 plus 1/2 plus 1/3 plus 4. Now it's alternating.
Well, doesn't it meet those conditions?
Does it meet both conditions?
It's decreasing and the limit.
So 1 over n, okay, that's a positive sequence. Is it at a decreasing sequence, condition 1?
Yeah.
Yeah. Does the limit of that go to 0, that sequence?
Yeah. It does.
Yeah.
It does.
Easy.
Therefore, convergent or divergent?
Alternating.
Convergent. Convergent by alternating series. So how is it that this one converges, but just the plain harmonic series doesn't? So what's happening here that makes this converge?
We're subtracting more than we're adding.
It's not about more or less. So this is convergent by the alternating series test because it meets the conditions. The Bn is decreasing and limit goes to 0.
We're never going to add more than the first subtraction. Like the first one chops the value in half.
Okay.
Like 1 minus half. And then we're only adding little bits and subtracting little bits.
Yeah, well, the point is that now every other one subtracts a value instead of adding on. So that's helping it to converge, because if you just keep adding, right? You just keep adding, you just keep getting bigger and bigger. And we know with the harmonic series, it gets too big, right? It gets too big. But now if you take every other one and subtract, what's going to happen? So we're at 0, we're going to add 1, and we're going to be at what? We'll be at 1. And then we're going to subtract 1/2. And where will we be now? At 1/2. And then we're going to add 1/3. Where will we be now? 5/6. Then we're going to subtract something. And then we're going to add something smaller than that. And then, so we're going to, it's converging in on some total sum here because every other term is subtracting. Instead of adding all the terms, every other one subtracts. And so that.
So then can we find that the number of to which everything comes to?
So we could get a really good approximation by having a large enough partial sum, right? Like, because these are all getting smaller and smaller. So if we say add the first 10 terms or the first 20 terms, it'd be a decent estimate. But we're not going to talk about a way to find the exact value. But just look at a partial sum with enough terms, and you can get it to within as many decimal places as you'd want.
So where are you exactly putting the values of n other than over n? Like, can you put 2, still get half, but do you multiply by -1? So that it's all alternating, and it's -10 instead of half.
So this makes the series alternate. When n is odd values, then this is +1, and when you have even values, you get -1. Right? That's what this does. That makes it alternate.
Right.
So formally, if we want to start with negative values, it's just -1 to the n. And
Yeah.
then if we want to start with positive, it's n minus 1.
Or n equals 0. Right? If you start with n equals 0, then you would get.
Sure. Well, we don't do n plus 1. Or can you?
N plus
Like -1.
Yeah, you can do n plus 1 too.
So there's no
Yeah, n plus 1 would give you the exact same thing. Yep. Okay. So that's the alternating series test. As long as you have, so this is kind of going against what we said before. All you need is the limits go to 0, and if you make it alternating, then that will converge. That's the alternating series test.
That's really cool.
And why? Because this opposite, you subtract every other term. So rather than adding indefinitely, you add, subtract, add, subtract, add, subtract. So that gives it a lot better chance to converge. Okay? And that brings up the idea of absolute convergence. So a series is absolutely convergent if I should have said a series doesn't need to alternate in order to converge. So this alternating is helping the situation, right? So if you took away the alternating effect, in other words, if you just made them all positive, absolute value of every term, and it still converges, then you didn't need that alternating to help it converge. And so therefore that's called absolutely convergent. It's convergent whether it alternates or not. That's the idea. Okay, so how about that? So the one we just looked at, is it absolutely convergent? No, because yeah. So you take away the. So basically, what we're saying is, then we're asking, in other words, what we're saying is the non-alternating version convergent? And it's no, right? That's all alternating. That's our harmonic series. We know that's not convergent. Therefore, this is convergent by the alternating series test, but not absolutely convergent.
And we can write ASD.
Sure. The convergence is dependent on the alternating effect. You have a convergent series that's not absolutely convergent. It needs the alternating to converge. Okay. How about -1 to the n, 1 over n cubed? Absolutely convergent? Yes or no?
greater than 1, yeah.
Gina, yes?
Yeah, it goes to 0 times to that.
Okay. What's that?
Because you have 1 over n to p and p is greater than 1.
P is greater than 1. So if you looked at, so we're asking then is, so yes, because the non-alternating version is convergent. P greater than 1. Okay, so then there's something called the ratio test for absolute convergence. And what you do is examine the limit as n goes to infinity of the ratio of the n plus first term to the nth term, the absolute value of that. And so we'll call this L, right? So that limit we'll call L, okay? So the limit, so you look at the ratio, the absolute value of the ratio of the n plus first term to the nth term, and you look at that limit as n goes to infinity. If L is less than 1, then this is absolutely convergent.
Whoa, that's pretty serious.
Pretty serious, huh?
Wow.
Okay, if L is greater than 1, then that is divergent. If L equals 1, then the test yields no conclusion.
There's some famous series out there that we just don't know what they do. That people are trying to crack.
I'm not sure about that. Yeah, I would guess that there's something.
Positive 1 series. I watched videos. Nobody knows what the answer is.
Send it to me.
Negative 1, 1, negative 1, 1.
Yeah. Watch a lot of videos.
Why is it not divergent?
I have no idea. Because I don't know.
That would be divergent because it's not. It doesn't get close to any particular sum. So I'm not sure about these videos you're watching. There must be more. There must be more to it than just that, because that what you described is divergent. Okay, so example. Negative 3 to the n over n cubed. So it's similar to the last one I showed, but the last one I had negative 1 to the n. Now it's negative 3 to the n. So that throws a wrench into things. So, but this is a good one to use the ratio test for. So we look at the limit as n goes to infinity. So using ratio test. And so what is a n plus 1? What is a n plus 1? So this is a n. A n plus 1 is? Right? Yep. Over a n. So now we're going to simplify this ratio and find this limit. Okay, so often you've got your sequence is a ratio itself, so we're going to invert and multiply. And if you want to start with that, start there, that's often saves you a step of writing. You can just start by writing this. You want to start by writing the multiplying by the reciprocal of the denominator, your an. You can start there, and that saves you a step of writing. Yeah.
If we've got those big absolute values on the outside, can we just kill the negatives?
Yeah, that's kind of what happens.
We can't do it outright.
Yeah, just do each one separately. Do each one separately. Okay, so if we have negative 3 n plus 1 over negative 3, what's that? Yeah, way to apply the absolute value until you've made some simplifications. Negative 3 to the n plus 1 divided by negative 3 to the n is just negative 3. If one more negative 3 in the top than you do in the bottom. And then we have n cubed over n plus 1 quantity cubed. And when you get this simplified enough, you evaluate the limit. So the second term, what's the limit as n goes to infinity of n cubed over quantity n plus 1 cubed? 1. We also know that that's 1. And so then we have negative 3 times that, and it's the absolute value. So this limit is? The limit is 3. Which is greater than 1 by the test then? This is? Divergent. So the alternating p series, where rank cube converged, but now it's like you multiply by a bunch of 3s and one more 3 every time you add the next term. Right? So this is you're also multiplying by n 3s in each term, and so that's why it's obviously going to diverge, because when you get to n equals 100, you multiply by 100 3s. So it's like. So now we're adding and subtracting, but it's by a bigger value every time, right? We're gonna add, and then we're gonna subtract an even bigger value. Then we're gonna add an even bigger value, 3 times as much, and then subtract by a bigger value, 3 times as much. So clearly this is gonna diverge.
So if n is equals 1 in the test, is no.
Yeah, if we got this limit to be 1, then we have to revert to something else.
Or we use a different method.
If there's a different test that might apply, or yeah. Okay, so let's try this one. Okay, so what do you notice about this one that's different than the other ones we've seen today? Besides it's more complicated.
We got 2n.
Well, got the n as a number down there.
Okay, there's lots of differences. Okay, so the difference I was thinking of was that it's not alternating. Okay,
Oh, yeah.
this one's not alternating. So because it's not alternating, if it's convergent, then it's absolutely convergent, right? So there's no conditionally convergent for this one
Oh, yeah.
because there's no alternating. So it's either convergent, i.e. alternating, or it's either convergent, meaning it's absolutely convergent, or it's divergent. There's no alternating effect. In this case, convergent and absolutely convergent are the exact same thing. Does that make sense?
Yeah, it does.
Yeah. Because convergent versus absolutely convergent is only in the case where you have an alternating series. So there's no alternating here. So this is convergent, then it's absolutely convergent. But I will go ahead and see if you can, by the limit, kind of group of things that are like together. So you're gonna have n squared, your n, all those n terms can group together. You get n squared plus 2n over n squared plus 2n plus 1. That goes to 1. And then you're gonna have 5dn plus 1 over 5dn gives you a 5. And then if you do the math right on this, you should have gotten 2 times n plus 1. Which is 2n plus 2. So when you distribute the 2, you get 2n plus 2 versus 3 to 2n. So that's 2 more 3's in the denominator.
So did it make you intuitively know what test is, or are you saying which one test I should be?
No, so that's part of like doing the integrals. After a while, so you're looking at, you come to a series, you have to know what applies.
Okay, then how do you know that it's the ratio? How do you know that?
I can do the ratio test for everything.